Hey everyone, welcome back to another lesson at MCV4U. Today we'll be looking at the scalar or Cartesian equation of a plane in 3 space or R cubed. So here, again, any vector that is perpendicular to the plane is a normal vector or normal to the plane. You can find the normal to a plane by finding the cross product, again, of the two non-collinear direction vectors of the plane. Since every vector in the plane can be represented as a linear combination of the direction vectors, the normal is perpendicular to every vector in the plane. So here, if we take a look at this first example, it says, find a normal to the plane with the vector equation r is equal to 3, 0, 2, plus s, 2, 0, negative 1, plus t, 6, 2, and 0, where s and t are an element of real numbers. So here what we see is, again, we have our two direction vectors. First one here, if we represent that as m1, again, we have that as 2, 0, and negative 1. And here our other direction vector would be 6, 2, and 0. And we can represent this by m2. And so here our normal to the plane. So vector n is to equal to m1. So here the slope, again, or the direction vector, m1 times, and the second direction vector, the second slope here, again, which is m2. And so here we're finding the cross product. So here we'll write down, again, our values that we have. So here we have 2 and 6 for our x values. For y values, we have 0 and 2. And then for our z values, we have negative 1 and 0. If you recall, when we look at the cross product, we're going to rewrite, again, the first two lines as well. So again, we'll rewrite 2 and 6, and we'll write 0 and 2, and we ignore the first line that we wrote. So we're going to ignore the 2 and 6, and then we will cross the rest. And so here, what we get as our values is we'll get here we'll get 2, negative 6, and 4. Here we can divide all of these by 2, which will equal 2, 1, negative 3, and 2. So here, the normal to the plane with this particular vector equation r would be at 1, negative 3, and 2. And so here we see that the scalar or Cartesian equation of a plane in 3 space is ax plus by plus cz plus d is equal to 0. Again, where a, b, and c is a vector normal to the plane, then a, b, c, and d are integers when possible, and a is greater than 0. So here it says, unlike the vector in parametric equations, the scalar equation of the plane is unique. So there's no such thing as a symmetric equation of the plane. So here, example number 2, it says find the scalar equation of the plane with the vector equation, vector r is equal to 3, 0, 2 plus p, q, 0, negative 1, and q, 6, 2, and 0, where p and q are an element of real numbers. So here we write our equation. So we have ax plus by plus cz plus d is equal to 0. Here, based on, again, what we looked at up top, Again, so here we'll get x minus 3y plus 2z plus d is equal to 0. And here we're given again our point of 3, 2, and 0, and then we'll use that to solve for d. So here again, we'll use point 3, 0, and 2 to solve for d. So here we have 3 minus 3 times 0 plus 2 times 2 plus d is equal to 0. Here we get 7 plus d is equal to 0, and therefore d is equal to -7. And so here, the scalar equation of the plane with this particular vector equation, remember we use pi to represent the plane. So therefore, again here, the equation in here would be equal to x minus 3y plus 2z minus 7 is equal to 0. Okay, so here example number 3 says the point A, 1, 2, and 2 is a point on the plane with the normal vector n is equal to -1, 2, and 6. And so here, again, these -1 represents A, -2, or sorry, 2 represents B, and 6 will represent C. Here it says, again, determine the Cartesian equation of this plane. Okay, so here, again, our equation of our plane, again, here is equals to -x plus 2y plus 6z plus d is equal to 0. Here we can again use the point that's given, which is 1, 2, and 2. Again, we'll to solve for d. So here we get -1 plus 2 times 2 plus 6 times 2 plus d is equal to 0. Here we get 15 plus d is equal to 0, and therefore d is equal to -15. And here we see that therefore, again, the Cartesian equation of this plane, or pi, will be equal to -x plus 2y plus 6z minus 15 is equal to 0. Here we'll here we want again a to be greater than 0, so we'll divide everything by -1. So our equation will be x minus 2y minus 6z plus 15 is equal to 0. Okay, example number 4 here again says determine the Cartesian equation of the plane containing the points A, -1, 2, and 5, and B, which is 3, 2, and 4, and C, which is -2, -3, and -6. And so the first thing we want to do is we need to find the normal. So we need to find the normal, to the plane. And we do that by solving for, again, the cross product of the direction vectors. And again, so those two direction vectors would be again vector AC, and vector AB. And so here, again, we see that vector AB would be equal, again, to B minus A, which would give us the point 4, 0, and -1. And then vector here, AC, again, would be C minus A, which would give us our point -1, -5, and -11. So here we'll find the cross product, again here, between AB, vector AB, and vector AC. Here, again, we'll write our values. So 4, -1, 0, -5, -1, and -11. Then rewrite the first two lines here. So 4 and -1, and 0 and -5. Again, ignore the first line here. And then cross, again, the rest. And so here, what we'll be left with is -5, 45, and -20. Okay, so here, that is going to be our normal. Again, that's equal to -5, 45, and -20. And divide all this by -5. It will give us 1, -9, and 4. And we're going to take this and we're going to sub this into the Cartesian equation. So here we have ax plus by plus cz plus d is equal to 0. So here we get x minus 9y plus 4z plus d is equal to 0. And here we see that we can sub in one of our points. We'll sub in 1, 2, and 5. So sub in 1, 2, sorry, -1, 2, and 5. And we'll sub that into our equation to find d here. So we have -1 minus 18 plus 20 plus d is equal to 0. Here we get 1 plus d is equal to 0, and d is equal to -1. And so here, therefore, our equation will be x minus 9y plus 4z minus 1 is equal to 0. Okay. So example number 5 says determine, again, the vector in parametric forms of the plane x minus 4y plus 3z minus 2 is equal to 0. So again, here it tells us to determine the vector, which means that we need to use the direction vectors and we need points. So again, we need direction vectors, which means that we need points. Okay, and there's two methods that, again, we'll look here. So here we'll grab this as method number 1. Okay, so here if we look at this first method, again, remember the intercepts that we can identify. So here, if we look at our x-intercept, and recall our x-intercept would be x, 0, and 0. So here, if we sub that into our equation, then we get x minus 4 times 0 plus 3 0 minus 2 is equal to 0, and therefore x is equal to 2. So therefore, we have our first point, which is 2, 0, and 0. Next, if we look at our y-intercept, remember that it's 0, y, and 0. So here, if we sub that into the equation as well, we get negative 4y minus 2 is equal to 0. So therefore, y is equal to negative 1 over 2. And so here we have our second point, which is at 0, negative 1 over 2, and 0. And then finally, our last one, which is our z-intercept. That's at 0, 0, and z. And so here that would give us 3z minus 2 is equal to 0, and therefore z is equal to 2 over 3. And so here, therefore, our third point here would be 0, 0, and 2 over 3. The next thing we want to do is we want to determine our direction vectors. So first, we're going to determine vector xy, which is equal to negative 2, negative 1 over 2, and 0. Here we're going to multiply everything by 2, and so we'll get negative 4, negative 1, and 0. And then our other direction vector, which is vector xz, which is equal to negative 2, 0, and 2 over 3. I'm going to multiply this by 3. That'll give us negative 6, 0, and 2. And then we're going to divide this all by 2. So that'll give us negative 3, 0, and 1. And so here, when we're looking at our vector equation, so this is going to be our vector equation. So here, represent that as in pi again. So here our vector r is equal to 2, 0, 0, plus s, negative 4, negative 1, and 0, plus t, negative 3, 0, and 1, which are our direction vectors. So then our parametric equation would then be for x, here we get x is equal to 2 minus 4s minus 3t. For y, we get 0 minus 1s plus 0t. And then z, we get 0 minus 0s plus 1t. Here we see that, again, we have our 2, 0, and 0. We have our negative 4, negative 1, and 0. And we have our negative 3, 0, and 1. Okay, so that's the first method. The second method, here we'll label as method number 2. Again, here in method number 2, again, we will always encounter 0 when using intercepts. Okay, so here, if we look at our equation, we have again x minus 4y plus 3z minus 2, which would be equal to 0. Again, what we want to do here is we're going to isolate for x. So if we isolate for x, the equation we'll get is x is equal to 4y minus 3z plus 2. And here we're going to rearrange for parametric form. Okay, if we rearrange for parametric form, we're going to let a few things. So we're going to let x is equal to 2 plus 4y minus 3z. We'll let y is equal to s, and we'll let z is equal to t. And here, again, we're going to fill in the spots for s and t and the constant. Okay, so here, then we can write again, x is equal to 2 plus 4s minus 3z. You get y is equal to 0 plus here we get 0 plus s plus 0z, and we get z is equal to 0 plus 0s minus 1. And therefore here we see that that was a parametric equation. Our vector equation here would be vector r is equal to 2, 0, and 0 plus s 4, 1, and 0 plus z. Oh, sorry, so plus here we'll do plus e negative 3, 0, and 1. So here this should be again plus 1t. And so here again we see that we have our 2, 0, 0, 4, 1, and 0. So 4, 1, and 0. And then we have again our final one here, which is negative 3, 0, and 1. Okay, so just some other properties of planes. So again here, if two planes are perpendicular, then their normals are perpendicular. To show that two planes are perpendicular, again, that means here the dot product. So dot product is equal to 0. If two planes are parallel, then their normals are parallel. To show that two planes are parallel, the normals are collinear. And so here, third, the angle between two planes with the normal vector n1 and vector n2 can be calculated using cos theta is equal to the dot product between, again, the two normals over the magnitude of the first normal times the magnitude of the second normal. So here, example 6 says determine the angle between the two planes. So here, plane number 1 is x minus y minus 2z plus 3 is equal to 0. And plane number 2 is 2x plus y minus z plus 2 is equal to 0. And so here, the normal, the first normal is it's going to be 1, -1, and -2. And here, the second normal is going to be 2, 1, and -1. The magnitude of the first normal is equal to the square root 1 plus 1 plus 4, which is equal to the square root of 6. And here, the magnitude of the second normal is equal to the square root of 6 as well. And so here, again, to calculate the angle, again, between the two planes, we have our equation here, which is cos theta is equal to the dot product, again, of the two normals over the magnitude of the first normal times the magnitude of the second normal. Here, then that's equal to 2 minus 1 plus 2 over square root 6 times square root 6, which is equal to 3 over 6. And so cos theta is equal to 1 over 2, and therefore theta is equal to 60 degrees. Example number 7 says show that the planes, again, the first plane here being x minus y minus 2z plus 3 is equal to 0, and the second plane, so this should be, again, the second plane, 2x minus 2y minus 4z plus 2 is equal to 0, are parallel but not coincident. So here, again, we have our first normal is equal to 1, -1, and -2. And our second normal, which is equal to 2, -2, and -4. Again, we see here that here we see that 2, second normal is 2 of the first normal. So if you multiply the first normal by 2, you get to the second normal. So here that shows us again that normal 1 is parallel to the normal 2. So here we write again our first plane. We have x minus y minus 2z plus 3 is equal to 0. If we multiply that by 2, see that we get 2x minus 2y minus 4z plus 6 is equal to 0. However, here we see that plane number 2, the equation is 2x minus 2y minus 4z plus 2 is equal to 0. So here, again, our d values are different, so that means they are parallel, but not coincident. Okay, then the last one here, example number 8, says determine the scalar equation of the plane parallel. So of the plane parallel to the xy plane through the point -7, 8, and 9. So here, again, that means the x-axis, again, here is perpendicular to the xz plane. And so here, that means our normal is equal to 0, 1, and 0. So here we write our equation. We have 0x plus y plus 0z plus d is equal to 0. Here we're going to sub in our point -7, 8, and 9 into our equation. To find d, we get 8 plus d is equal to 0, and therefore d is equal to -8. And so therefore, our scalar equation of the plane parallel to the xy plane passing through the point -7, 8, and 9 will be y minus 8 is equal to 0.